drinking and drugs and driving, for example, that combination, and a car accident and so on, or some other progressive disease like muscular dystrophy and so on. So a lot of possible reasons why these individuals can have communication issues, and those can be target patient groups for a brain-computer interface. So let's look at an experiment we did many years ago with a locked-in syndrome patient, someone who was completely paralyzed after giving birth to her third child. She had a massive stroke in the brain stem. She became completely paralyzed. And you see also an artifact, the head is moving, is oscillating, and that's something that is not under her control. And she's focusing on particular characters on the screen, and you see a lot of flashing rounds here, intensification rounds. It's a patient for sure, but of course 10 years ago the technology was not, the algorithms were not that powerful yet, and you needed, like, what was it, 20 or so intensification rounds to produce one character. And you see the B was already, now it will be O, I think, yeah. So she's typing bonjour, hello in French. Okay, so this is of course what it was so many years ago. We did 10 years ago one of the very first studies on these kind of patients. So you see here a number of patients with one with ALS, another with a stroke, bleeding in the brain. So different types of stroke with different types of diagnoses and age groups and gender. And then the next slide shows for these 8 subjects the result. You see the number of intensification sequences and accuracy plotted for all these subjects, and different types of classifiers. We will not go through them. Some of you recognize here the LDA that we discussed before, and the support vector machine is another one, and there are other types of classifiers. As you see, they don't really matter that much, but what matters is how the accuracy is evolving as a number of intensification rounds. And you see, for some subjects, whatever you do, it doesn't seem to go beyond, in this case, 80% accuracy. From other subjects, they reach 100%, so they look like pretty normal, like a normal healthy subject. But you see a lot of patients have issues in terms of achieving a good accuracy level. For example, patient 7 that's really problematic for that person. Like 1 out of 2 characters is wrongly typed. So this is sort of why is that? Of course, it could be due to the limited attention span, as some patients cannot pay attention for a prolonged moment, and that will affect the performance. Of course, if you lose your ability to concentrate, then of course then it collapses. And the technique relies on it. The paradigm relies on your ability to pay attention to the target, to the flashing of the target, but also things that are related to the medication that is the patient is receiving, that could affect a number of things that are happening in the brain. So it is a difficult. As soon as you're working with patients, it becomes a lot harder, the whole thing, to achieve performance. Then we did some error analysis, and this is what I just indicated. The plots shown here on the next slide. You see the black square in the middle is the target, so to speak, and you see the artifactual stuff here surrounding. You see that you get a lot of if there is flashing happening in the neighborhood of your target character, you get side effects. You get artifacts due to that, and of course these artifacts go down as you're further away from your target target character. So this shows that indeed you can benefit from a scrambling of your matrix. The matrix is here just according to the alphabet. If you scramble that and you reduce the occurrence of flashings in the neighborhood of your target character in a word, when you're typing a word, then you can benefit from that. So this was for the different classifiers, and you see it's similar disadvantage. Okay, next slide. It shows that you can do something similar for auditory stimuli. We were working with the flashing on the screen, so visual stuff. You can also work with auditory stimuli, in this case beeps. So you instruct your subject to pay attention to a particular beep, and it could be like pa pa beep pa pa, and that beep is the target, and you take that up in a paradigm. Now, if that particular target beep is appearing, you see a deflection in the amplitude of your EEG signal that peaks here later than the visual. It's more like 450-ish millisecond instead of 300-ish milliseconds. Because it's auditory cortex. The pathways are longer. Probably it has a number of effects there on the involvement of that amplitude deflection. And then you have also an N2, but N2 you also have in case of the P300 actually, but we didn't talk about it. So this is a typical pattern that looks like a P300, but it is a bit shifted in time. And you can work around that, and here it indicates the significance in difference between the non-target and the target response. So there is indeed something to be said about it. Of course, if you develop your algorithm, you have to check a bit if what you're detecting is also correct in terms of the scalp distribution. You're going to check that in terms of your electrodes and in terms of your detection algorithm. What sort of weights are attached to your different electrodes. You can do that checking there to see if you're working with the right stuff. So this is then a paradigm that combines visual support with the auditory. So the auditory support, the auditory paradigm is used in locked-in syndrome patients. It's a usual paradigm for them, and they use maybe four different types of beeps to select characters and stuff like, or commands more. It's a very limited, a very slow way of communicating, but if you have that patient before you and that patient is virtually or practically blind, then auditory stimuli are probably the only way to make it work. And it's mostly used in these patients to figure out if they have the ability to pay attention, or if they have any cognitive abilities, let me put it this way, that they can pay attention to one particular beep given other beeps. And the fact that you can't communicate otherwise with these patients, then this is a way of checking if they are still able to discern, if they can pick up auditory information, they get structured, and they can use it to select a particular beep against other beeps. So to make it work in a spelling setting, these people here, these researchers, have provided some visual support. So you have the regular matrix of characters of the alphabet, and you number these rows and columns as indicated. And then you see with the little loudspeakers there are beeps given. So you can have, instead of flashing the rows and columns, you have a column selected, so to speak, but then with a particular beep. A row can be beeped as well, let me put it this way. And of course, if you're focusing on a particular character, it means you have to focus on beep corresponding to column 7 and the beep corresponding to row 1. And at that intersection, you have character B, if that is of interest. So this is how it works. And then next slide, you see the results. So they did just where the subject needed to remember the rows